So, that's enough information to determine the area of this. Well, that's enough information to just determine this triangle, right? If you know two sides and the angle at which they meet, you know the triangle. So it's enough to know the area. What's the formula for the area of this triangle?
1/2 E times sine.
Yeah, except I think my letters don't line up with yours. Nice. So there's one of the formulas we got yesterday. And we'll use that to do some things today. There's one other result we got last time. We called it the law of sines. What does the law of sines say in this situation? Well, maybe I'll start with this because, it's called the law of sines. It's going to involve some sines. I'll start with that.
It's not like the sine, one length over sine. No.
Yeah, let's write that one. So side length divided by sine of angle opposite. And what does it tell you about these things?
We need to see you can solve for the other, like C length. Okay?
Yeah, so you could solve for any other length given some information. Because the law of sines says that that ratio is the same no matter which corner you look at. Like somehow this quantity is just about the triangle. It's not about the rest of stuff. It's the same no matter which corner you look at. And sometimes it's nicer to write it like this. Sometimes it's nicer to write it with the trig functions in the numerator. It's the same equation either way. So let's use this to do something. I think we made it to the point where we had set up a solving a question last time. And then we talked about how we could do it, but we didn't have time to actually do it. So let's now come back to where we were in the notes.
Do you have any more of the,
Oh, yeah. Anyone else need? All right.
Thursday or Friday, so.
That's right. Cool. So here was the setup. There was some tall object we wanted to determine the height of. So there's a height we want to know. But I don't have a tape measure that's tall enough to measure the height of a building. So what did I do instead? I had someone stand next to the building with a 2-meter stick. I stood some distance away. I didn't bother measuring how far away because it was hard to measure because the building's on a hill or something. And I measured some angles. I measured the angle of elevation to the base of the meter stick, to the top of the meter stick, and then just to the top of the building. Filled those into this diagram, and then you can determine all the other angles because angles in a triangle add up to 180 degrees, and when two angles add up to a straight line, well, a straight line makes 180 degrees. So we could extract this pink triangle because I know a side length in this pink triangle, and I know all the angles. So extract this pink triangle, copy down all of its numbers, you get that. And there's a side length that looks useful to determine. What does the law of sines let you say about solve? Give me an equation from the law of sines that involves this side length x.
Sine of 80, or x over sine of 80.
Cool. Side length divided by the sine of the angle opposite equals. Now give me a side length you do know in this triangle. 1. And it's in meters, but we can just remember that it's in meters. And what is the angle opposite? that look like something we could solve for x? Yeah.
Isn't it supposed to? Is it supposed to?
Yep. Yep, it is. And that's exactly the type of error that happens when you like try to wrap things up in 30 seconds. I appreciate you catching that. Anyway, that looked like something easy to solve for x. Yeah, just like multiply the denominator over to the other side. X is equal to 2 times the sine of 80 degrees divided by the sine of 5 degrees. And so on the one hand, like we could get a decimal approximation of that, right? We have access to calculators. It might be helpful to do so, but like this isn't the final answer anyway. I guess this x tells me how far away I'm standing from the base of the building. So I'm stalling right now, hoping that someone tells me a decimal approximation for that. About how far is that?
I think it's 22.59.
You said 22.59? Nice, and it's in meters. So, you are apparently about 23 meters from the base of the building, in terms of straight line distance. All right, that feels pretty good. That's not what we wanted anyway. I didn't care about this, like this length isn't the problem. I want the height of the building. That's the height I want. So now here's what I'm going to do. What did we just find? We found that side length right there. Can you now look at that diagram and see a triangle where you know at least one side of that triangle that involves the height? Yeah. There's the length you would like to know. I know this length because it's the length that's in this triangle. Oh, cool. So it looks like the triangle from you to the bottom of the building to the top of the building is a triangle you can use the law of sines on again. So let's use the law of sines on that again. So let's start by filling in like the angles and stuff in this diagram. What's this angle? I think it's 50 because like it's hard to read, right? This whole angle is 55 degrees. And then you go back 5. All right, so this is the trouble with I messied up that diagram a bunch and then waited like 5 days and then came back to it. So this is an angle of 50 degrees. This one. This one. It's this angle, right? Which, and the angle on top. Is, yeah, it's unlabeled right now, but we could figure it out. I heard a 35? Do I hear a second for 35? Cool. Angles in a triangle add up to 180 degrees, so I'm not going to do the arithmetic. All right. This is the one that I want to know. This one, that side length I already know. It's that number, which is complicated looking, so I'm not going to write it down. I'm just going to remember that I know what x is. I'll plug in that value for x once I'm ready. So let's use the law of sines again. Should I use height as a variable name, or should I give it like a single letter variable name? Cool. The height is h. H is the length I want to know. Let's use the law of sines to tell me something about h. So what's the angle opposite h? 50 degrees. So h divided by sine of 50 degrees equals, I know the side length x. What is the angle opposite x? 35 degrees. That's something you can solve for h? Yeah, let's solve it for h. I guess you have to do the exact same thing as we just did to get x, right? I just need to move that sine of 50 degrees to the other side. H is equal to x times the sine of 50 degrees divided by sine of 35 degrees. Feeling pretty good so far? And we already know what x is. So let's just plug in the exact value for x. Write out an exact thing, and then we'll use a calculator to get a decimal approximation for the height. That seems sensible? Yeah, let's do that. So I know what x is. I'm not going to use this. I'm going to use the exact value so I don't lose any information. Whenever you take a decimal approximation, you lose some information. So let's use the exact value. I think I wound up with 2 times the sine of 80 degrees. That's divided by the sine of 5 degrees, and this is all multiplied, so I can just put that sine of 5 degrees in the denominator. Multiplied by sine of 50 degrees, all over sine 35 degrees. And that degree sign next to that 5 is a little bit too big. I plugged that all in correctly? Cool. So what is that?
I got 30.1.
Cool. So apparently this building is about 40.2 meters tall. Does that feel pretty okay? Nice. And this is, in fact, the mathematics that the surveying tools that you see, like people in brightly colored vests with those devices on tripods pointing them at things. This is the trigonometry that makes those devices work. Those devices can measure an angle, and then you can tell them what some heights are. Once they do that, they can crank out these distances. In fact, say instead I wanted to know how much rope I would need to put into a grappling hook gun to get me from where I'm standing to the top of the building. Could I do that using this diagram? Yeah, it would just be determining that side length from where you're standing to the top of the building. It'd just be another random law of science. Neato. Cool. Folks feeling pretty good? All right. So this is probably the strongest application of the law of science. You can use it once you measure some angles to just extract a bunch of side lengths. But you can also use all of these formulas in some other ways. You can use it to determine angles. If I asked you to solve this for the angle C, you could, right? You would multiply the 2 to the other side, divide by those two side lengths, and then you just need to undo the sine with an inverse sign. Of course, there's always some weirdness when you undo a sign, right? There's this plus 2 pi k that shows up, and also the two different solutions. There's arcsine and pi minus arcsine. So we'll have to think about that too. Let's do exactly that on this next page. So here's another example we're going to go through. Nice. All right. So I'm going to write down a sentence that is the whole point of this page in that top, I think, once I get there. But let's start. Here is an example. Here is a triangle below. Here's the thing I'll tell you about it. The area is equal to 4. If you want to put some units on this, put some units on it. Yeah, I got one of those big ones. Anyone else need notes for the day? All right. So let's write down an equation that governs this. So given the facts in this picture, what equation does the area formula give you? Yeah, nice. So you know these two side lengths. You know the area. So that means 4 is equal to 1/2 times side, times 2 times 5 times the sine of this unknown angle alpha. All right. Cool. I'd like to know alpha, so let's start by determining sine of alpha. Think you can tell me what sine of alpha is? Does anyone want me to do the walk of determining sine of alpha? Cool, then I will. So I just need to get sine of alpha on its own. So maybe I'll start with this before I do any algebra. 2 times a half is 1, so I can cancel those two. And now I just need to divide the 5 to the other side. So it looks like I am getting 4 over 5 is equal to the sine of alpha. People agree? Awesome. I want to get alpha by itself. There's the obvious solution. Arc sine of 4/5. All right, hold on to that for now. There is this weirdness whenever you use inverse sine to find an angle. Like, it could be that, or it could be that plus 360 degrees.
So would this be like the reference angle?
Yeah, this would be like a reference angle. It's like, it's some angle, it's like in this quadrant because it's inverse sine of a positive number. Let's see, if I add 360 degrees to that, is that still an angle you're allowed to see inside of a triangle? No, right? The biggest angle you can see in a triangle is smaller than 180 degrees. If I subtract 360, then I'll have a negative angle. That doesn't make sense in a triangle, so I don't need to worry about that. But there is the angle that's in quadrant 2. Because you can see an obtuse angle inside of a triangle. In fact, let's see 2 solutions to this triangle problem. I have a little Desmos interactive. So, let's see. There we go. So what were the 2 sides in this triangle? So side 1 is 5, side 2 is 2. Doesn't matter which one's which. What was the total area now? 4. Do those look like 2 different triangles? They both have length 5, length 5. They both share this side in common, so they both have this side length of 2. Do they both have the same total area? They have the same base length, right? And they have the same height. 1/2 base height. They both have the same area. There are 2 different triangles that solve this problem. And let's just pay attention to the angle around that origin point. So in the purple triangle, what can you tell me about the angle at this origin? Is it acute or obtuse? Acute. Let's draw the other triangle. Acute or obtuse? Obtuse. This angle might be obtuse. So here is the situation. There's the angle that inverse trigonometry tells you. So here's the fact. Angles inside a triangle might take any value between 0 and 180 degrees. Or between 0 and pi radians if you want to walk in radians. So I'm looking for, so there's the graph of sine of x. I want an output value of 4/5. How many different input values give me an output value of 4/5 in that picture? 2. So there might be 2 options that we have to worry about. So there are 2 options we have to consider. Let's determine them. So one of them we already have done, right? There's the piece of sine that you use to get inverse sine. So I know what this point is. This point is the arc sine value that we just found. So the first one, the one that inverse sine tells you, is arc sine of 4 over 5. The second choice, well, I don't know, like, people have their inverse trigonometry notes on them? What is the second solution?
Is it pi minus 1?
Yeah, pi minus the forced solution,
Oh, yeah.
which is probably what you meant. I don't think you literally meant pi minus 1. So pi minus arc sine of 4/5. This will be the obtuse solution. Should we be in radians or degrees today? Anyone want to be in degrees? Cool, let's also put this in degrees. Pi radians is how many degrees? 180. So 180 degrees minus arc sine of 4/5. Nice. That gives us these two different angles. That's the number of solutions I expect to see to this triangle problem. So these are all of the possible solutions. Nice. And this link, in fact, goes to that Desmos demo that just pulled up. So here's the big takeaway. Whenever you use inverse sine to solve a triangle problem, you have to worry about whether or not an obtuse angle is possible. Because arc sine will never tell you the obtuse possibility. Because the range of arc sine is negative pi over 2 to pi over 2, so negative 90 degrees to 90 degrees. It'll never give you an angle bigger than 90 degrees because it can't. So if the solution is an angle bigger than 90 degrees, arc sine will never tell you. So to find it, well, you need to worry about two possibilities. There's the acute option. The acute option will be arc sine of whatever it is that sine of alpha was supposed to be. The other one is 180 degrees minus that. And there's this boxed if right here. Do you think if I give you absolutely every situation involving triangles, that obtuse angles will always make sense as options? Sometimes they will. There might be situations where you just already know there's one angle you already know is obtuse in a triangle. Can a triangle have two obtuse angles? No, you like start drawing a picture and try, right? Say, well, there's a side length, there's an obtuse angle, there's an obtuse angle. Oh, they're not going to meet. So there can only be one obtuse angle. If there is an obtuse angle, it'll be opposite the longest side length. So if you already know that the side length opposite this angle is like short, then you know that this angle can't be obtuse. But if you can't rule it out, then you have to worry about that possibility. So here's the main point of this page. Regardless of if you're using the area formula or the law of sines, if you use arc sine to get an angle in a triangle, you need to consider whether that angle may be obtuse. Which is just code 1 for bigger than 90 degrees, right? Groovy. So, as we've just seen, whenever you use the area formula to extract an angle, it might be obtuse. Or it might just not exist. Do you think I could have set this up differently so that this instead said that sine of alpha is like 5 over 4 instead? Yeah, right, if I just like ratcheted up this 4 to 10 instead. I guess it wouldn't be 5 over 4 then, it'd be like 10 over 5. Still, that's bigger than 1. So you also need to worry, does this say that sine of alpha is bigger than 1? If it does, there are no solutions. So let's see some more examples of this sort of stuff happening. So here is the next flavor of triangle problem. This is a side-side angle triangle. I know two sides and then the following angle. This is enough information to determine the triangle again. And let's try to do it. So right now the only tool we have is the law of sines. The law of sines works really well when I know a side length and an angle opposite. Do I know a side length and an angle opposite in this triangle? Yeah, I'm not looking at it, but if I designed it correctly, then I should. So I know this pair. Let's use that. And I'm going to use the portion of the law of sines that has the angles on top instead of the angles on bottom. Just because I'm going to want to determine an angle, it'll be one fewer step if I do that right now. So, sine of 60 degrees divided by 10 equals. So now, take a look at that. Is there one other fact you know about this triangle that we haven't used yet? There's the side length of, is it? Yeah, say it.
Bottom length.
Bottom length is 11. So I should be able to use that to determine this. Don't know this, don't know this. So law of sines on its own won't help me find either of those, because there would be like two unknowns in that equation. But if I know this angle and this angle, well, they add up to 180 degrees, so I can figure out that angle, little a. And then I can worry about big A when I get there. So let's write this step down. So this should be equal to the sine of C divided by 11. All right. Yeah.
Does it matter what form you put it in? Because you see how like it's A for the side and the order.
Yeah, so it doesn't. Because if I just like take the reciprocal of everything in sight, they're all still. Yeah, you can write down this equation with the signs on top instead of the sides on top. And it's like nothing deep. It's just like, if you didn't, then step one would be change this equation to write it in that form. Groovy. Now that I have it in that form, is that easy to solve for the sine of little c? What do you get? So I'm not solving for c yet. I just want the sine of little c. Is equal to I just need to like cross multiply, right?
11 times 60 divided by 10.
Nice. And 60 degrees is an angle you see on the unit circle, so we could get like a more simplified exact value. But I think that would just like disguise stuff more than it would help us. So let's just leave that as is, and let's just ask one question. Give me a decimal approximation for the right-hand side of that equal sign. Give me 0.95. Is that a valid output value for sine? Yeah, it's less than 1, right? In fact, that tells me a lot. It's almost 1, so this angle is going to be like pretty close to a right angle. So let's find the acute value. So what's like the obvious value that little c might take? So what's the obvious way to figure out what c is given that information?
You take the arc sine of that.
Yeah, take the arc sine of the right-hand side. That'll give you the acute solution. So the acute value for c is arc sine, or sine inverse, because I haven't given myself enough space, of the right-hand side. 11 times, well, you know what? Maybe I will. No, I won't. Sine 60 degrees all over 10. feeling pretty good? All right, then let's get a decimal approximation because the notes ask for one. So let's compute arc sine of 11 times the sine of 60 degrees divided by 10. All right. Do you think I want the answer in radians? I have other angles in degrees, so I should probably get this into degrees. And because I don't want to faff about figuring out how to get it to correctly convert from degrees to radians, I know the conversion factor, right? Multiplied by 180 divided by pi. You have a handheld calculator that you can split in degree mode. That agree with answers people got?
As long as the arc sine, can I just do 1 over?
You should probably have a sine inverse button. Is that a... Oh, you're using like your cell phone calculator.
I think I do it on my...
Yeah. The cell phone calculator you can't use on tests anyway. 72.3 degrees. All right. So that is the acute possibility. Let's take a look at that triangle and answer the question, is it possible that the angle A, nope, the angle C might be obtuse? And here's the way to decide. If an angle is obtuse, then the opposite side has to be the longest side. Is it possible for the side opposite A to be the longest side of this triangle? Yeah, 11 is bigger than 10. And I don't know the other side, so I can't compare those. So, might A be obtuse? Yes. Might C be obtuse? Yes. So, I've already gotten the acute option. Sine inverse of 11 times the sine of 60 degrees all over 10, which we just computed to be about 72.3 degrees, right? How do you get the obtuse option from the acute one? Flip to the previous page if you need. Pi minus that, except I'm in degrees this time, so 180 minus that instead. All right. Feeling pretty good? So, those of you who are playing along with a calculator that has like a built-in memory function, like you could do 180 and then scroll up to the previous answer, right? And I'll do something like that. So there is the acute option, 180 degrees minus that stuff. Ah, son of a diddly. All right, so it's at that stage that the Google calculator starts breaking down and deciding that it doesn't want to parse out my expressions anymore. Wolfram Alpha is also annoying in ways because it really wants to walk in radians instead of degrees. All right, 107.7-ish? That agree? Nice. 107.7 degrees. All right. So now, we know the angle C. Well, we know it's one of two things. It's either that acute angle or that obtuse angle. In each case, could we determine the other angle? Yeah. In fact, what I might even do is this. I have this exact value, but it's going to be like annoying to keep on saving and reusing that in every step. So I'm going to do something that I often tell you not to do. I'm just going to remember the decimal approximation right now. So, to get the angle A, that will be 180 degrees minus 60 degrees minus C, which is about 180 degrees minus 60 degrees minus 72.3 degrees. Seem like something we can do? Yeah. And as long as I still have it built into my this, let's do that. So I wanted 180 minus 60 degrees, and then minus this arc side of whatever. I get 47.7. That agree? All righty. 47.7 degrees. In the obtuse case, do it yourself. Did you do the same thing in the obtuse case? Nice. You just have to subtract a different number. And I'll point something out about that when you get it. I mean, I didn't walk it out, so I can say that wrong.
12.3.
I hear 12.3 degrees. Do I hear a second? All right. So if you walk out the exact answer as well, you'll notice that these two things will add up to something interesting. In this case, it looks like they're adding up to 60 degrees. Oh, there's a 60 degree somewhere else in this problem. I bet there's a pattern you could notice out of that. Neato. All right, let's determine the side length. So the only thing left in the list to determine is the side length A. Is the side length A. So let's try to work that out. So I guess you just did the obtuse one in this case, so maybe I'll do the obtuse. Well, maybe I'll see what people want. Do people think that they know enough that they can determine the side length A in each of these cases on their own right now? Anyone want me to go through one of them while talking? Cool. I will then, I guess, go through the obtuse case. Those of you who want to walk independently or semi-independently, do the acute case in parallel. So, let's see. A is the side length that I want. There's what I want. Do I know the angle opposite? I do, right? It's the thing that we just found. So let's write that down. A divided by the sine of little a is equal to, and now I guess I have some freedom. I can use any pair consisting of a side and angle opposite and write down another equation. And so you could use the 11 and the angle C. I'll discourage you from doing that because the angle C we have right now is approximate instead of exact, so we get like more on everything else. I know the exact value, the given value of 10 and 60 degrees. 10 divided by sine 60 degrees. Probably like something we can solve for big A? Yeah, nice. So, do that. Semicolon, capital A is equal to, I guess I just need to get that denominator to the other side by multiplying. 10 times sine of little a divided by sine of 60 degrees. And I have a decimal approximation for little a. A is approximately 10 times the sine of 12.3 degrees divided by sine of 60 degrees. Groovy. And we have calculators, so Let's get a decimal approximation. 10 times sine of 12.3 degrees divided by sine of 60 degrees. 2.46-ish. That agree with what other people have? Did anyone do it where they just saved mod decimal places in the angle little a? Yeah.
I had mine like flipped, so like my lengths were on the bottom and my degrees were on the top, and I got a different answer.
Ooh, let's talk through. So you wrote down sine of little a over big A equals sine 60 degrees over 10. So talk me through your steps. What did you do to this?
Well, I put in the angle we got for A, and then I put it down with the 10, so it was sine 60 over 10 times sine 12.3.
Sine 60 degrees divided by 10.
And I got
A is
4.
fewer things twice, so I'm just going to write little a. And what was the other side of the equal sign? It's going to be 1 over a. That a is still in the denominator. So that's the point of starting with it in the numerator, so you don't have to deal with it. When you do encounter something like that where the thing you want is in a denominator, cross-multiply to get it out of the denominator. Neato. Ruby. Folks feeling good then? I'm going slower than I wanted. I'm almost out of time. So those of you who use the law of sines to find big A in the acute case, what did you get?
8.54.
Do I hear a second? Cool. See some heads nodding? It was basically the same walk, right? The only difference is like what got plugged in here. So I guess in this case you wound up with A approximately 10 times the sine of 47.7 degrees divided by 11. And then you said that's about 8.54? Oh, I didn't actually write down the decimal approximation in the obtuse case. $2.45, $2.46. Neato. That seemed pretty okay? So there are some other weird cases that might happen. And I'm going to accelerate just a little bit now. So here is another triangle problem. We won't have enough time to go through all of it, but really quickly we'll get to the point where something unusual will happen. Is this still itself? What angle would you want to use the law of sines to find first in this problem? C. It is an unknown angle that's opposite a known side. So you'd wind up writing down sine of little c divided by 3 is equal to sine 60 degrees divided by 4. Do some work. Sine c equals 3/4 of the sine of 60 degrees. And either by getting a decimal approximation or just by thinking about it for a second, is that going to be less than 1? Get a decimal approximation if you want. Cool. It's less than 1. You got a decimal approximation, so tell me what it was. Nice. Less than 1. In fact, it's 3/4 of something that's less than 1. So it's going to be even smaller than something that's less than 1. So that's a valid output for sine, so there's going to be at least one solution. Let's ask ourselves, might the angle C in this problem be obtuse? So that's the angle we're trying to find. There's the side opposite. Now remember, if the angle C were obtuse, then the side opposite would have to be the longest side. The side opposite little c, is it even possible for it to be the longest side length? No, there's a longer side length. 3 is less than 4. No. C is not opposite the longest side. So there is no obtuse option. Do you think we could do the same walk as last time to get the acute option? Yeah, I mean, we could. I'm not going to because I have 5 minutes left. People think they could do it on their own time? Yeah, we've already found the side, well, we've already basically found the side length little c. It's just going to be arc sine of whatever that is. Once you know the angle little c, get the angle little a. Once you know the angle little a, use law of sines to get the side length big A. One more triangle problem. Let's jump down here to see the last weird thing that can happen. Let's try to go through the same walk. I'm going to ask you to now solve this triangle problem. You'll notice that there's less space given. We won't need that much space this time. So let's start with the same process. What's the angle that you would want to find first? Still little c. It's opposite a side you know. Sine of little c divided by side you know is equal to sine 60 degrees divided by 3. Easy to solve for the sine of c? Nice. Let's solve for the sine of c. I guess we need to multiply both sides by 4. And that's it. So sine of little c is equal to 4 times sine 60 degrees divided by 3. And give me a decimal approximation.
It's gotta be bigger than 1, right?
How do you come to that conclusion?
Well, 4/3, if you're multiplying by 4/3, it's like compounding it.
Yeah, it's going to make it bigger. Sine of 60 isn't bigger than 1 is. So there's some possibility that it might not be bigger than 1. But like when you compute it, what do you get?
1.1. It was over 1.
1.15.
Nice, 1.15. I guess that 1 should round up to a 2 then. The point is that's bigger than 1. That's bad. What's the biggest value sine can ever be? 1. Unless you're allowing for a complex angle, and I don't know what it means to have a complex number as an angle in a triangle. So, are there any solutions to this problem? So I guess did something bad happen? Yes. Sine of c is bigger than 1. This has no solutions. Yeah.
Can you explain again, why something bad happened, or why it can't, or it has no solutions?
Yeah. So the equation that we wound up writing down right here. So it got messy, so I'm just going to rewrite it. Sine of c was equal to something that was like 1.15, you said.
Yeah.
Is sine of an angle ever equal to 1.15? No. But sine of c is always less than or equal to 1. So this would be like when you encounter something that says like x squared is equal to negative 5.3.
Mm-hmm.
If you're not allowing complex things, you automatically say there are no solutions, I'm stopping.
Okay.
So as soon as you see something that says sine has to be bigger than 1, you should stop and say there are no solutions. Groovy. So, with my closing minute, I'm going to point out that there are like 3 cases that you might see whenever you're solving a side-side angle triangle. And there's a rough flowchart down here to think about. Whenever you want to solve a side-side angle triangle, locate a pair consisting of an angle and a side, both of which you know. Next, locate an angle that you don't know opposite a side you do know. Now you can use the law of sines to write down an equation. you'll get sine of b equals some stuff. I'll just put a star there. No, star's already in use. That's labeled with a triangle. You can figure out what sine of b has to be. If this previous line says that sine of b is bigger than 1, then you're done. You should just stop and say there are no solutions. If b is not the longest side length, then you only have the acute option. Inverse sine, whatever it is that you said sine is equal to. Otherwise, you should use 180 degrees minus the acute option to get the obtuse option. And you'll have two solutions. And from there, just follow your nose. Find the rest of the things given those assumptions. So here is what I would like you to do in advance of tomorrow. Here are 3 triangle problems. Don't solve them. Just use this flowchart and tell me how many solutions do they have. Each of these are a multiple choice. The answers will either be 0, 1, or 2. Coincidentally, there are 3 examples. So be prepared next time to answer that last example. And ideally, between like now and tonight, I'll get a review for midterm 3 posted.
Is the inverse sine and arc sine the same thing? Okay.
Yeah, and depending on what like computer system you're using, you might be using any of those things.
Okay.
What button do you see on your calculator? Arc sine or
the inverse.
inverse sine? Okay.
Is there any time after like 4:30-ish I could swing by today or tomorrow? That's better.
I'm usually gone by 4:30.
That tomorrow Friday
Okay. Yeah. So here are the things I would encourage. I'm reasonably responsive to email. Like if you send me an email at like 8 at night, I'm probably gonna not look at it.
Yeah.
But if you send it by like 6, I'll probably send a reply tonight. I'm always in my office by 8 a.m. So if you want to, don't try to talk to me tomorrow at 8 a.m. because I have like a meeting at 8 a.m.
Okay.
But yeah, otherwise like Friday, if you want to come by Friday.
Okay. Perfect. Thank you.
So I have a field trip, so I'm going to be gone Friday, Monday. I'll send you the phone and stuff.
Okay. Have you looked at what you missed on those days?
I have not yet.
Okay. Let's stop recording.